Hello guys, welcome to the Python series. In today's video we are going to talk about what are bitwise operators. So first let's get to know what is a bitwise operator. Bitwise operators are used to perform bitwise calculations on integers. The integers are first converted into binary, which is represented in ones and zeros. Then the operations are performed bit by bit. Hence the name can be confirmed as bitwise operators. When the result is returned in decimal format, bitwise AND operator returns 1 if both the bits are 1, else the output would be 0. If either one of the bit is 0, then the total output would be 0. Here is a table comprising about all the bitwise operators. First we have the AND operator, sets each bit to 1 if both the bits are 1. If either one of the uh, bit is 0, then the whole thing is 0. The next operator we have is the OR operator, sets each bit to 1 if one of the two bits is 1. If either one of the bit is 1, then it's fine, so the output will be given as 1. The next operator is a XOR operator, sets each bit to 1 if only one of the two bits is 1. The next we have the NOT operator. It inverts all the bits. So for example, if your input is 1, so the output would be 0. So it's just the reverse of what you have given the input as. Next we have the zero fail left shift. Shift left by pushing zeros in from the right and let the leftmost bits fall off. So here it shifts the value to the left. So here when you're shifting all this thing, it shifts all the zeros and pushes off all the zeros and gives you the valid input. The next we have the signed right shift. Shift right by pushing copies of the leftmost bit in from the left. So it pushes off all the bits which are zeros from the left and only considers the values from the right. Into bitwise operators in Python, first we have to get to know how do we convert a given integer into binary format. So in order to do that, so why do we have to convert a given integer into binary? So binary computers are operated or stores data and perform calculations based on binary input, which is made up of zeros and ones. So in order to communicate with the computer, we have to convert any given integer and we have to communicate using binary. So first let us take any given integer. So let me take an suppose I'll take an integer 49. So I have to convert this given integer into binary. So basically a given digit in binary is represented by a bit. So a byte makes up 8 bits. So let us consider those numbers. So we have 128, then 64, then 32, then 16, then 8, 4, 2 and 1. So here is the 8 digits which we can consider to be as 8 bits. So how do we come up with these numbers? So basically 1 is nothing but 2 power 0, 2 power 1, 2 power 2, 2 power 3, and this is 2 power 4, this is 2 power 5, 2 power 6, 2 power 7. So here we can see that these numbers, these powers of 2 can be given to get this numbers. So how do we come up with this integer 49? So let us consider those numbers which can be summed up and we to get 49. So let me take 32, then 16, then 1. So when we sum up these given numbers, it would give us 49. So it is 32 plus 16 plus 1. So when we add all this together, we would get 49. So which is 32 plus 16, 48, and plus 1, 49. So now let us consider all the numbers we have considered to be as 1. So we have considered 32, 16 and 1. So we'll take these as 1. So all others are zeros. So this is 0, 0, 0, 0. So this is how we come up with the binary format for a given integer. So the binary format for this given integer 49 is 00110001. So now we are going to do some examples on bitwise AND. First we have a variable a as 49. We have already found out the boolean um, format for the integer 49. So next we're going to take b as 5, and now we're going to use the a and b. So here we are seeing that the output is 1. So now we'll find out how we got this output to be 1. So here you can see this is the boolean table for the bitwise AND operator. So first we have two inputs, and based on these inputs we are going to get the output. So first, when we have the input 1 to be 0 and input 2 0, the output would be 0. Input 1 0 and 1, and the output would be 0. So if either one of the inputs are 0, then the entire output would be retrieved to be 0. So here the in third case we have 1 and input to 0, so the output is 0. So the last case we can see that both the inputs are 1, so hence the output retrieved would be 1. So now when we consider the both the inputs we have found for to retrieve the integer 5, so let us write down the values for the given selected in values. So here for 4 and 1, so these both are ones, rest all are taken as zeros. So this 0 0 0 and 0. So hence we got 0 0 0 0 0 1 0 1. So when you try to use the bitwise AND operator, so we are going to use the bitwise AND operator. So here both of the inputs are 1, so it is 1 0. So if either one of them is 0, so the entire output would be 0. So 0 0 0 0 and 0. So hence 1, which is also 2 power 0. So 2 power 0 is nothing but 1. So when we find the bitwise AND for 49 and 5, we would get the value 1. So previously we saw that when we took the bitwise AND of variable a and variable b, we got the output to be 1, which is 49, and 5, which is 1. And we have seen that in binary format that how we got the bitwise AND for these two variables. So next we are going to see the OR operator. So we're going to take in the same set of values for a and b. So we are going to try the OR operator for a and b. So here you can see that the value for a or b is 53. So now let's see that how did we retrieve 53, and let's look at the truth table for the OR operator. So here you can see this is the truth table for the OR operator. We have two inputs, input 1 and input 2, and the following output. So for input 0 and 0, we would get output as 0. So if either one of the inputs are 1, then the output we would get is also will be equal to 1. So here in the second case we have input 1 0 and input 2 as 1. So the one input value is 1, so the output would be 1. So the third case we have input 1 as 1 and input 2 as 0, so the output retrieved would be 1. And the fourth case, input 1 is 1 and input 2 is 1 and the output is 1. So if both the inputs are 1, then also the output would be 1. So now let's look at how we get the OR operator. So first we have 49 and next we have 5. So now we have to find the OR of 49 and 5. So we know that the binary of 49 is 0 0 1 1 0001. So this is the binary format we found for integer 49. So 5 for 5 is 0 0 0 0 0 1 0 1. So when we find the OR of these two integers, so when both the inputs are 1, so it would be 1. Here both are 0, so it is 0. So here any one of the value is 1, then we will get 1. So it is 0 1 1 0 0. So when we want to find the value, which is 2 power 0 plus 2 power 2 plus 2 power 4 and 2 power 5, so it's nothing but 1 plus 4 plus 16 plus 32, which is which is 53. 1 plus 4 plus 16 plus 32 is 53. So hence we found out that when we find out the OR operator by using the OR operator for this variable integer 49 and the second integer 5, we would get the value to be 53. Previously we looked at bitwise OR operator. So we had first integer to be 49 and the second one to be 5. So we found out the bitwise OR for a 49 and b 5, which turned out to be 53. So now next operator we are going to look into is the bitwise XOR operator. So I'm going to take this same set of integers 49 and b as 5. So next we are gonna use the XOR operator a. So here you can see by using the XOR operator we are getting the output to be 52. So let's find out how did we get this, and first let's look at the truth table of the XOR operator. So next let's look at the truth table for the XOR operator. So first we have the input 1, input 2 and the output. So for input 1 0, input 2 0, we have the respective output to be 0. So here in this case also, if both the inputs are 0 or both the inputs are 1, then the respective output would be 0. Other cases it is 1. So for second case, input 1 0, input 2 1, the output is 1. And here for input 1 1 and input 2 0, the output is 1. For the last case, when both the inputs are 1, the output is 0. Let's find out the binomial for XOR operator. So this is our 49 XOR 5. So we know that when both are zeros or 1, then the output would be 0. Other than that, for other cases it is 1. So both are 1, so it is 0. So 1. So it is 0. For this is 1. So sorry. So for this is 0 1 0 1 1 0 0. So it's nothing but 2 power 2 plus 2 power 4 plus 2 power 5, which is nothing but 4 plus 16 plus 32, which is nothing but 52. So here we have the final product of 49 XOR 5, which gives you 00110100. This is the binary expansion for the given product. So we get 2 square plus 2 power 4 plus 2 power 5, which is 4 plus 16 plus 32, which gives 52. So here you can see that the variable a, which is assigned with 49, and b with 5, when we have the XOR of a XOR b, we got the value to be 52. So hence, by using the bitwise XOR, we also found out like how we expanded 49 and found out the binary expansion of 49 and binary expansion of 5, and found out the product of these two integers, and then we got the output to be 52. So last time we looked at the XOR operator, where we took in the first variable a as 49 and b as 5, and we retrieved the output to be 52. So the next operator we will be looking at is the NOT operator. So a NOT operator uses unary operand, which contains only one operand. So basically when we have and when we have an input and we have an output. So here, if our input is 1, so the output will be just the reverse of what we have in the input, so it would be 0. So if the input is 0, then the output would be 1. So this is what we can find in the truth table of NOT. This is the truth table of the NOT operator. So how do we get that? So let's look at this. So if our a is 49, so we are just going to use the negation symbol. So here we are getting the output to be 50. We'll see that how did we get this minus 50. So hence, in order to do that, actually negation a can be written as minus a minus 1, which is nothing but minus 49 minus 1. So this, by doing this, we get our output as minus 50. So by doing this, using the NOT operator or using the negation symbol, we can find that negation of a, which is our input, is equal to minus of a minus 1, which is minus 49 minus 1, which is minus 50. This is how we retrieve the output for the NOT operator. So now how do we find out the binary form of minus 50? So how do we find the binary form of minus 50? So now to do that, let me first take find the binary. So let's write down the binary for 50. So for 50, the binary can be written as 0 0 1 1 0 0 1 0. So first we find the negation of 49, which is 0 0 1 1 0 0 0 1. So now we'll just find the negation of this. So here 1 becomes 0, 0 becomes 1, 1 1 0 0 1 1. So here we are this is the complement of the binary form of 49, which is just the reverse of 14, just the reverse of 49 what we got. So now how do we find for minus 50? So in order to do that, we'll just take this number and find the complement of that. So basically we have 0 0 1 1 0 0 1 0, and when we find the complement it is 1 1 0 0 1 1 0 1. So this is the complement of 50. This is actually the binary form of plus 50, and by doing the complement we can find out the complement of minus 50. So now we are going to look at bitwise left shift operator. So first let us take an integer as equal to 15, and we are gonna say a is less than 3. So here a represents the value and 3 represents the number of ships we are going to take. So I'll be showing you how to do that manually. So here we are getting the output as 120. So what the required number we are taking is 15. So for the number 15, the binary form would be 0 0 0 0 1 1 1 1. So what we have to do here is we have to do the bitwise left shift, and we're gonna discard the first three elements, and rest all we're gonna just take these ones and we're gonna drop it here. So it's going to be 0 1 1 1 1 0 0. So hence when we so this is 2 power 3, 2 power 4, 2 power 5 and 2 power 6, so which is nothing but 64 plus 32 plus 16 plus 8, which is nothing but 120. So this is what we have got here, a less than 3. This is the bitwise left shift where we are shifting 3 units to the left, and the output we are getting is 120. So here you can see that the output we retrieved is 120 by just shifting and just discarding the first three element and shifting these to the left, and just adding another set of zeros onto the end of this form. So this is about bitwise. Now we're going to take the same integer a is 15. We're going to take a as 15, and now we're going to operate for bitwise right shift, which is a greater than 3. Here you're getting the output to be 1. So let's look at how we should do and how to find out this manually. So let us take our number to be 15, and we know that 15 is 0 0 0 0 1 1 1, and now what we are going to do is we are discarding the terms this outside, and we're just gonna take this and put it here. Yeah, so it's nothing but we're gonna put this to the right, which is 1 0 0 0 0 0 0 and 0, which is nothing but 2 power 0, which is 1. So hence we saw that by doing the bitwise right shift, we are going to shift all the bits which are there on the left to the right, and the last three digits or the bits on the right would be discarded, and the left ones would be shifted to the right. So as we saw here, for bitwise right shift greater than 3, we got the output 1. So hence by using manual method we confirm that we get this to be 1. So if we are finding it difficult to find out these manual methods and want a way just so that we can get directly, so we can use two built-in options operators which can directly give you the binary format of a given integer by saying that I want the binary of suppose I'll say 15. So here it will give me the binary form of the integer 15. So I can also convert this binary form back into the integer by using another built-in operator int and specifying the binary input. So by doing this, I can see that I'll retrieve back the integer what I have mentioned here. So these two built-in operators can be easily used to find out the binary form of a particular integer.